Okay, so we're just going to spend a minute right now talking about pressure vessels and how they work. And so if you've ever worked with a pressure vessel, you can understand how if you apply a pressure inside this tank. Now we have a couple of tanks here. You have a cylindrical tank, and over here is a spherical tank, or a basketball, or whatever. So if you apply a pressure inside of a tank, you fill it with air, there's going to be some stresses that are applied on the surface, on the walls of the tank. And so we can actually figure out what those stresses are. So if you have a certain pressure, and our pressure in this case is going to be P, if you apply a certain pressure, then you have a circumferential stress on this cylindrical tank, circumference stress, and you have axial stresses, and they're not quite the same because of the geometry of this tank. They're going to be a little bit differently. And so if you ever microwaved a hot dog or anything like that, you can you know, like if you microwave a hot dog too long, it's going to split right down the seam, right down the middle. And a hot dog is basically a pressure tank. And so what you get is that you get this tank that just breaks like that, or whatever. You can imagine it long ways. This is the length of the tank, and it splits open that way. And that is because the circumference stresses, the stresses that are going this way, are a lot greater than the stresses that are going this way. In fact, these are twice as great. And so we're going to say, like, this is 2 times the stress, while this is the stress. And so it's going to break in this way first. It's going to split rather than actually popping open, because that stress is a lot greater. And so these are the equations that we use for this. The circumference stress is PR over T, P being the pressure, R being the inside radius of the tank, and T being the thickness of the walls. And then your axial stresses are PR over 2T, so it's about half of the circumference stress. Now if you have a spherical tank, all of your stresses everywhere is equal, and it's all going to be axial stress. It's all going to be PR over 2T. And so as far as being able to hold more air or more pressure, your spherical tank is actually a lot more efficient than your cylindrical tank. Fun fact. And so that's pretty simple. You can actually go in pretty easy. You know what the pressure is, you can plug it in and find your stresses. There's another thing that I wanted to talk about real quick. I'm going to erase all this stuff. I'm going to erase this as well. But now remember, the circumference strength goes around the hoop, and axial goes, you know that. Draw those arrows real quick. Okay, so those stresses still work the same way as a normal stress. And so you can imagine that if I were to take this tank, the pressure, you could, if like this tank was held together by glue down the middle, and I wanted to find out how much force was in that glue, we could look at it like this. There's a force, the pressure is causing a force to push on it, trying to push this side of the tank away. And there's also got to be a force inside the walls that are resisting that. So the two forces, this force and the forces in the wall, have to be equal to each other, because we know it's an equilibrium from statics. And so thereby we also know that the stress in the walls, and you can imagine the walls of that tank over there. Actually, let me draw them. Yeah, so you have stress in those walls. Now the stress in that wall, we know that it is equal to, and it's axial stress, so we know that that stress is equal to PR over 2T, right? But we also know that that stress is also equal to the force over the area of the tank. And so we can actually find out how much force is being run through the glue that's holding this tank together. Now, I don't know why you use glue to hold the tank together, but in theory, well, let's figure that out. So if we know that the pressure is, we'll say that the pressure in this tank is 10 psi, P is equal to 10. We know that the stress is equal to 10, and we'll say that the radius, we'll say the radius is 5 inches. The diameter of the inside of the tank is 10, so the radius is 5 inches. R is equal to 5 inches Okay, 5 divided by 2, and the thickness we'll say is equal to 0.2 inches. T is equal to 0.2 inches. So that thickness is 0.2. And so we know then that the stress, well, you can go and you can plug that in and figure that out. But we also know that that force, that's equal to the force over the area. Now that's the area of that ring, that the cross-sectional area of that piece, and that's a ring that looks like this. So you have an outside radius and an inside radius. And so your area would be pi times the outside radius squared, and the outside radius is 5.2 inches, I think. 5.2 squared minus the inside circle, which is 5 inches squared. So it looks something like that. So you plug that all in, you know that the force running through the inside of that tank has got to be equal to, the force is equal to 801 pounds. So there's 801 pounds of force running inside that wall, or pushing on it in the circumferential direction. Awesome. And that's a pretty basic overview of pressure vessels and how they work.